So previously, we've worked with problems in 2 dimensions. So that means that y changes based on x. Or sometimes it's been t, sometimes it's been a different variable, but it's always only been one variable. So for example, we've had things like this is x, this is y. We've had things like this is t, this is y, whatever. Sometimes, however, both x and y are changing based on a third variable, typically t. So that might look something like this. Notice it's not a function at all. It's actually something called a parametric equation. And what's happening is that if we think of some third variable t, as t changes, you can imagine this is like a little bug crawling around or something like that. Both x and y are changing as that bug crawls. For example, let's imagine that we say we have a dog who's running around a tree in a circle that has a 1 meter radius. The dog's position in the x and the y direction changes based on time. How long it's been running determines where it is in the circle. Furthermore, x and y change in a systematic way. If we have information about the dog's x position and its y position, and how quickly it's moving in the x direction, we can draw conclusions about how quickly it's moving in the y direction. In fact, mathematically we can write an equation for this circle that the dog is drawing. It would actually be x squared plus y squared equals 1. And even though that's not a function, it is a relationship between x and y. That leads us to related rates and equations. If 2 quantities are each differentiable with respect to time, and can be related using an equation, then we can take the derivative of that equation with respect to time to get an equation that relates the rates of change of the 2 quantities. And we're going to see how to do that in a minute, but the first thing we have to do is review a prerequisite skill for these types of problems. When you take the derivative with respect to a different variable use a special version of the chain rule. So let's do some examples with that. Notice here on the left I'm going to write our normal type of derivative. These two variables match. So that means we just use our normal rules, bring down the 2, subtract 1 from the exponent, that's 2t. However, what if we do this instead? Notice how these don't match. That means we're going to take the derivative like we normally would, but this is now a box function. Any variable that doesn't match what's in the denominator of the dd whatever, that's automatically a little box function. So if we bring this as 2y, now we have to use a chain rule. We have to take the derivative with respect to t. This means derivative of y with respect to t. Because we don't know what it is, we're just going to leave it That's all that implicit differentiation really is. It's an addition of the chain rule whenever you have variables that don't match. So let's do some other similar ones. We can do the derivative with respect to t of 3t. That's our standard rule. This is just 3. That's going to be just 3 as well, but because there's a y here and these variables don't match, we have to also do the chain rule, derivative of y with respect to t. Just like that. ddt of t equals 1. ddt of y equals 1 times dy dt. That's all it is. One thing to be aware of is that just like the normal chain rule, if you are needing to do something like this, where you're going to be doing the chain rule when you do this derivative, you're going to multiply the entire thing by the derivative of what's inside the function, just like you would normally. So this is the same thing as finding the derivative 1 plus t to the 1/2. So that equals 1/2 1 plus t to the negative 1/2 times the derivative of 1 plus t. That derivative is just 1, so it's just like that. Over here, same idea. Now this derivative would just be 1, except that because the variables don't match, we've got to do that little funky chain rule. Right like that.